Hey everyone, thanks for joining. Today, as part of this presentation, we'll be talking about how multimodal LLMs are improving and transforming the industry recommendations at scale. At a high level, today I'm going to talk you through the comprehensive journey of how these reasoning-based approaches work in multimodal systems. We'll cover both the theoretical foundations as well as practical realities of deploying these systems at scale. So let's start by examining fundamental paradigm where we are witnessing that moving from simple correlation to reasoning based capabilities. How does these empower the models to improve and figure out more details based on user engagement patterns? These help drive state of the art performance in recommendations. Next, we'll ground this in reality with academic studies and concrete results, including recent results from publications across ACL and NACL and the recent 2025 papers. We'll then shift to practical applications, examining real world case studies of deploying these at scale, covering both significant benefits and challenges companies are facing today. Finally, we'll conclude with honest assessment of the current limitations of these systems and promising future directions. Great. Starting out, here's the paradigm shift. How we are moving up from correlation to causation. For years, recommendations has primarily been about pattern matching, finding correlations in user data, and this has worked scalably well across billions of user interactions every day ac- at large recommendation systems. LLMs introduce a new paradigm. What if we could reason about user activities and learn more from them? Instead of just matching what users did, LLMs can deduce intent from complex contextual queries. And we have some examples, including Amazon. Today, how do they do it with the knowledge graph? The shift isn't just theoretical, it delivers a significant 15 to 25% performance boost. Here, we'll try to see essentially in the traditional pattern matching, we have statistical correlations. We find that users who bought X also bought Y. So this is essentially a correlation between collaborative filtering, where we have seen this worked well and scale across multiple use cases. However, a lot of these systems struggle with novelty and context, and thus they have a limited understanding of what essentially is going on in the entire system, and the system is stuck in a feedback loop. Compared to what we have with LLM powered reasoning, we understand the content and causality as to why is something happening and what could be the reason behind it. For example, if a user searches for a rainy weather hiking, it's likely that they are looking for waterproof shoes. Now, this is something we could get from correlation if we have a lot of user data. But example, if this is something, and if this is a new category or a cold start, we need LLM powered reasoning based on world knowledge to be able to discover and make a first concrete guess. This would essentially enable the system to really make a good recommendation even for the cold start users and cold start items. Essentially, what this helps us is handling complex multi-step queries, and we have seen the results across industry where this leads to 15 to 25% uplift. Now, the breakthrough in multimodal reasoning, let's look at how does this work. So the breakthrough in multimodal reasoning does not just come from throwing more data at the problem. It's fundamentally deriving from thinking how do we structure the reasoning process itself. Starting off, we had something like Lava in this field, and Lava Chain of Thought was a very phenomenal paper where instead of solving complex multimodal problems in one shot, they broke it in 4 stages. So we have had chain of thought reasoning in text-based approaches. The multimodal reasoning focused on how can we take the same approach and take it multimodal. So let's think of it like a detective's methodology. What Lava COT enables is let's summarize what one sees, then describe the visual evidence, then reason through the logic, and finally draw the conclusion. But here's the key innovation. At each stage, the paper presents multiple candidate solutions and then uses beam search to select the best path forward. This single algorithmic change gave them 7.4% performance boost, which is massive. So this is about the algorithmic change. Let's look at the architecture changes. The second primary breakthrough was in solving the attention problem. Previous models treated different modalities like separate conversations happening in parallel. The new approach lets queries from the text attend to keys and values from the image. So essentially, we have cross-modal attention. This truly integrates the conversation where visual and textual information learn from each other. This semantic aligned approach takes this further and makes sure that we are able to really identify fine-grained understanding from the image and reason it and ground it in the textual queries. Finally, we have temporal reasoning improvements. For temporal reasoning, we have a lot of recent work, including chain of thought VLA, as well as more recent Vision R1, which use causal attention when predicting future states, but only when, but making sure the full attention is being used when making the decisions. This enables the model to reason about sequence of events across the entire videos. Essentially, what led to SOTA performance in multimodal reasoning? The core insight behind the SOTA performance is that we need to separate thinking from the answering. This two-stage rationale, like answer the architecture first by generating detailed reasoning chains, and then explicitly connect information across the modalities. And then we use these rationales to guide final answer generation. This actually mirrors how humans solve problems. We don't just blurt out answers for the challenging problems. We work through the reasoning step by step. And what's remarkable is that this structured approach reduces hallucinations because the model has to justify its reasoning using self-reflection and then commit to the answer. In terms of improvements, we have multiple benchmarks where we do see significant gains. All of these improvements together directly translate to measurable performance gains. We have gone from about 35 to 40% on mathematical visual reasoning to about 49.9%, which is very near to the human baseline of 60%. On document understanding, we have achieved almost 94.4%, which is essentially human level performance. Um, we also have other benchmarks like MMMU, where we have models approaching 76.1%, which is just a human expert level performance. This just shows that we are not just improving incrementally, we are approaching the threshold where these systems can augment human reasoning in professional contexts. Now let's look at how do these reasonings help in recommendations and what do the industry, before going to the industry, let's look at what do academic papers talk about and the approaches they have shown to be promising. So Reasoning Rec, this was published in NACL 2024. They focus on curating gold, um, gold standard reasoning chains from Mixtral and show that this high quality reasoning data can push up the performance of the models on different metrics across such as AUC and BERT score. The key insight from the paper is that using semantic information um, based on user profiles as well as item description enables creating more richer reasoning chains. So essentially what they end up doing is use a very good language model like Mixtral and augment the user profile as well as item descriptions, and then use these details to create very rich reasoning chains as to why a user would likely interact with a given item. They showcase a positive correlation between AUC and reasoning quality reflected by BERT score and demonstrate that better reasoning directly translates to better recommendations and not just explainable ones. Next, we have RecSaver, also published last year at ACL. They take the fundamental challenge in recommendation problem and reduce and take a different approach, where essentially instead of relying on a very expensive model, they focus on how can they have a very good quality reasoning chain generated without human curated explanations. So instead of focusing on a very expensive model, their innovation is in generating coherent chain of thought reasoning autonomously. So essentially, the model generates multiple such chains and focuses on the ones which are most consistent. So they showcase that this approach achieves 15 to 20% improvement as part of their AUC and F1. And the most compelling part is that their generated reasoning shows strong correlation with human judgment. So apart from just the metrics, they have human evaluations on both faithfulness and coherence of this chain of thought reasonings. This suggests that the model isn't just improving metrics, but is actually developing reasoning patterns that aligns with how humans think about the recommendations, and they're found to be coherent by the labelers. Moving to more recent publication, we have something published in 2025, which is latent R3. This represents a cutting edge of latent chain of thought reasoning with end-to-end fine-tuning for GRPO. GRPO was published as part of DeepSeek models, where they use this approach to fine-tune the model end-to-end, and is shown to be very efficient. What's fascinating is that their finding shows that reasoning improvements are more pronounced for unpopular items compared to the popular ones. This is what we would see from a reasoning based models, so that they can mitigate the popularity bias and showcase good improvements for the torso and long tail of items, which usually are getting neglected in statistical pattern matching approaches. Finally, a lot of these papers, as well as similar ones, showcase that reasoning isn't just transforming traditional vision and language tasks in LLMs, they're also fundamentally improving how we understand and predict user preferences across the domains. Now, this is what we understood from the papers. However, can we apply this entire reasoning, these approaches at scale? Let's understand what are the challenges and what are the benefits of applying these at scale in an industrial use case. We see that there is a clear trade-off between performance gains and operational costs. Let's look at real-world economics of how this plays out. Starting off with pros, we essentially see that pass at one is much more valuable for high throughput and is very crucial for production systems. There have been a lot of recent papers which do showcase that reasoning models or reinforcement learning essentially just make sure that pass at one improves, whereas pass at k essentially remains the same as the base model. Why pass at one is very important for recommendations is that it enables us to have very good solution in the first pass, which means that the model can get and arrive at good predictions for high throughput use cases. This dramatically reduces the computational overhead per successful outcome. The performance gains in NDCG and hit rate translate directly to business metrics. What it means is that we have better recommendations. It means higher user engagement and higher revenue. At the same time, there is a much softer benefit which is equally important. We do see that user trust increases significantly when systems can explain their reasoning. Instead of treating it as a black box, people can understand why they are getting a certain recommendation, and they can understand how their behavior is impacting the recommendations that they actually see. We do see there is a 40 to 60% improvement in user satisfaction scores when explanations are provided alongside the recommendations. Now, this creates a feedback cycle where better explanations leads to more user trust. Users spend less time guessing or understanding why a certain items are recommended to them, and they rather engage with things which are more intentful and providing more valuable value to them. Now, this leads to much cleaner training data and model performance over time. Finally, reasoning models demonstrate that genuine world knowledge and behavioral understanding helps them to handle the edge cases and novel scenarios, which are definitely not possible with the statistical pattern matching approaches. Let's look at the cost. Like, what are the cons here? Uh, the cost here is absolutely substantial. We are looking at roughly at least 10x training compute requirements compared to standard models. This is not just taking a bigger model, though that's a major part of the equation. It's also about complexity of the training reasoning chains across modalities. We also have significant improvement in latencies, typically 1.5 to 3x, which can be deal breaker for real-time applications like recommendation systems and search. Memory requirements also are a major limitation, where we do see that bigger models need very complex system setup to be able to scale and serve them to multiple users. Most critically, out of all these system challenges, these systems are massively inefficient for simple use cases. For example, if a user is searching for something simple, using a reasoning model is not the most optimal solution for that setup. Essentially, it's an overkill. So scalability concerns are around how do we make sure that we do well for easier queries while using the reasoning models for handling the challenging problems and scale them. This requires a thoughtful deployment and understanding what are the how do we sort of understand the system and user patterns and deploy these systems so that they complement each other. Now, there are three high level paradigms in how these reasoning applications can be applied at scale. Let's start off with custom architecture. First of all, custom architecture optimization is essential for learning at scale. Taking off the shelf reasoning models and expecting them to work efficiently in production environments is not going to scale. So there are companies who are developing specialized architectures and optimize the reasoning process itself. They focus on techniques like sparse attention patterns, dynamic routing, and how can we have hierarchical reasoning chains. We'll go through a case study of Meta developing a similar sequence reasoning model for ads in the later slides. The key insight here is that not every reasoning step requires the same computational intensity. By designing the architecture that can adaptively allocate compute based on the problem complexity, we maintain the reasoning quality with reasonable trade-offs. And this essentially helps us reduce average computational costs. Next up is how do we have the entire system integration to be more efficient? Rather than replacing the existing systems at all, the winning approach is how do we merge LLMs with existing infrastructure like knowledge graphs for efficient inference. We do have a use case, a study case for Amazon, where Amazon uses the knowledge graphs merged with LLMs to handle nuanced interpretation and explanation generation. Uh, Further, caching is another popular choice where for reasoning systems, because for complex queries, we have overlapping components. By caching intermediate reasoning steps and popular complex queries, we are able to dramatically reduce the latency for common use cases while maintaining the full reasoning capability for novel scenarios. This helps us get the best of both the worlds. And finally, distillation. This is a very popular paradigm where distillation to ranking and retrieval models solves the latency problem pretty elegantly. We use the large reasoning models as teachers to generate high quality label data and then train smaller, faster retrieval models such as two tower or even ranking models, which are deep and wide networks or even sequential networks. These smaller models achieve real time latency while benefiting from the reasoning insights of the larger teachers. The approach is pretty successful and is deployed in recommendation systems across multiple companies, which we'll go over in upcoming slides. Essentially, what it shows is that reasoning at scale requires these hybrid architectures. Let's look at them in detail. The first one is sequential learning for ads recommendation at Meta. Essentially, Meta identified that the current set of model architectures had limitations in scaling up. A better approach was instead of having manual feature engineering, how about we have event-based multimodal feature representation? This enabled the entire system to be more end-to-end optimized based on how these event-based models can represent each of these events uniquely. These event-based tokens were then fed into a custom transformer architecture, which is optimized for learning user behavior modeling. Essentially, what we do is we scale the representation learning so that we are able to capture user interactions at a higher fidelity. The existing models had some pooling approaches, which was replaced with a new architecture which could learn the feature interactions from unpooled embeddings. The prior system on the left-hand side uh, was based on aggregated features and was highly optimized for fixed-length embeddings, which was a limitation. The new approach with sequence learning introduces new challenges where different people can have different event length, longer variable sequence, and these represent challenges in how system can be optimized across a lot of these use cases. To handle these cases, the team has focused on PyTorch optimizations to handle and support JAG tensors. There are some kernel level optimizations to process JAG tensors on GPUs. And finally, a flash attention to be able to handle these JAG tensors. Next up, let's look at how Amazon handles merges LLMs with knowledge graph for common sense reasoning. Essentially, Amazon developed a Cosmo framework which leverages large language models along with knowledge graph to understand common sense implicit relationships from customer interaction. Um, Essentially, Cosmo involves a recursive procedure in which LLMs generate a hypothesis as to why a particular interaction is happening and what could be the common sense reasoning behind it, what the user is searching, and what is being purchased. This, combined with human annotation and machine learning models, filters out the low quality hypothesis and enables the system to generate very high quality hypothesis as to what is essentially a intent of the query is. Now, these set of high quality data is then being used to train the system and showcase a high quality recommendation to the users in when they search for it. And the paper claims that this helps them improve the search query performance by up to 60%. Another use case is at Indeed, where they reduce bad job matches in the recommendation. Essentially, what they find is implicit engagement based negative signals are not sufficient and biased, uh, primarily from the users who provide very lot of feedbacks. Um, to be able to counter this, the system required a lot of human labeling, which was not very scalable. Instead, what the team did was use LLMs as a cost-effective ways to identify high-quality label data, which can help identify the jobs which are not high quality and then can be easily targeted as the ones which can be rejected from being recommended to the users. Uh, they found that the out of box performance for GPT-4 was good, but it was also very expensive. Essentially, what the team did was find distill from GPT-4 to GPT 3.5, which helped them achieve similar performance as GPT-4 out of the box. However, this system was also not scalable enough to be deployed in production. They further distilled it down to a e-bad match model, which is essentially a bird based model, which enabled them to have a very online real time inference. They showcase that this approach led to significant improvements from 4 to 11% in their apply rate and reduced the low quality job postings. A very interesting use case is how do we use LLMs and their world knowledge to improve the hybrid query recommendation system. This was a paper from Spotify. Essentially, they identify that query recommendation is pretty important for users to be able to explore and identify content. As part of this work, they developed a doc to query system, which expanded queries candidate set and reduced the retrieval bias. Essentially, they used LLMs to understand what are the different things that user could search for given a particular search query. They found that this helped the users ex- express more complex queries. So they found the query length increased from 10% on an average to maximum 30%. And it also helped them improve the performance on exploratory queries by about 9%. So, as a summary, what do we see across all of these? That vanilla application of reasoning models is not feasible. However, industries are finding a way to blend the efficiency of pattern matching with reasoning to get significant wins in real time systems and deliver improved value to the users. However, let's look at what are the limitations of the current approach and what would be a future direction look like. So, the distillation approach that we discussed, it hits a hard wall when it comes to complex open-ended reasoning across modalities. We can distill a reasoning model's ability to rank movies or recommend product, but we cannot distill its capacity for creative problem solving or novel multimodal synthesis. Essentially, what is currently happening is that we are training from the reasoning based models down to a very simple model, which is learning new set of pattern matching based on these reasoning answers. This is a limitation of the current approach, uh, and we need to identify ways on how we can get above it. The next step is visual temporal reasoning challenge. The visual temporal reasoning represents our biggest scaling challenge. Processing video sequences with reasoning chains requires enormous computational resources, and we are talking about these reasoning over hundreds of frames. With limited inference budgets, companies are forced to choose reasoning depth and temporal resolution. Thus, most production systems cannot handle these sophisticated reasonings on multiple frames in the videos. For the task performance, we do see a clear performance dichotomy emerge. Current reasoning models excel at structured tasks like mathematics and coding. We do see from a lot of papers on GRPO, DPO, and a lot of recent work where we do see significant improvements in Maths 500 and coding tasks since there are logical frameworks and verifiable answers. But these models struggle significantly with puzzles, creative tasks, and truly open ended problems. A more recent paper from Apple showcases that a lot of these models have limitations in solving puzzles, even though they are very easy. This showcases that our reasoning architectures are still fundamentally pattern matching at a very high level rather than exhibiting genuine creative reasoning abilities. Further, the primary limitation in the recommendation system is lack of calibration issue. A lot of these models showcase performance collapse at complex tasks, which reveals a inference time scaling limitation. As reasoning chains get longer, accuracy doesn't just plateau, it often degrades, as shown in the Apple paper. Perhaps most concerning is the missing confidence calibration, which is very important for recommendations. These models can produce very elaborate reasoning chain, which can sound convincing, but it could lead to incorrect solutions. And also, they lack the self awareness to recognize when the reasoning is not right. We need these self reflections to be really good and confidence calibration so that recommendations can truly become independent without human intervention. So these limitations kind of define our next frontier. How do we develop reasoning systems that maintain accuracy at complexity scales and can handle truly open-ended problems and know when to express uncertainty about their own reasoning process? Thank you. That's all the things I wanted to share.
Great. Thank you so much, Aashu, for the great talk. Audience, please share your questions in the QA section. Sorry. So I have a few questions. Actually, I will start so that the audience can also share their questions in the QA section. So in terms of the benchmarking these multimodal models or foundation models, do you think current benchmarks bias towards vision-heavy tasks or language-heavy tasks, and how we can address that?
Yeah, that's a very good question. I think there has been a lot of study where benchmarks like Science QA and other benchmarks
Mhm.
very lean heavily towards world knowledge. So even if you don't look at the visual cues, you can answer them just based on the pre-trained knowledge.
Right.
So there is a lot of work around improving the benchmarks so that the model really learns to focus on visual details and then not just on the pre-trained world knowledge. So that's definitely a work in progress.
Right. And you mentioned reasoning in the latent spaces, right? It's a new and upcoming topic. Can you give us some insight and compare it with text-based, like chain of thought reasoning, and in terms of especially interpretability of what's happening in the latest space in terms of reasoning?
Yes, I think it's a relatively recent trend where people are looking at how do we reason in the latent space. You bring up a very valid point that interpretation is likely lost. However, there are use cases like, let's say, recommendation systems where we do not really need the model to spend as much tokens to drive the reasoning chains. So I would say interpretability is the biggest bottleneck here, but also being able to make sure that we are generating the right reasoning chains based on latent reasoning is a work in progress. A lot of these optimizations just happen end to end, so we do not really understand if this is reasoning or are there other things happening in play due to better optimizations.
Right, excellent. So one more question from me. Do you think that VLMs are capturing implicit signals in the data, like emotional tone or aesthetic preferences in the user item interactions, or they are looking more at the concept levels?
I would say it depends on the use case. So if there are use cases where the task kind of requires the models to reason about the aesthetic appearance of a video or an image, or essentially thinks about, essentially, let's say we want to identify if it's a
Mhm.
um, mocking video, then the models learn to attend and like what does the audio tone represent? Is it mocking? Is it funny? So I think it is kind of task dependent, and
Mhm.
the models are capable of doing that. We have multiple omni-modal models, which they kind of take the image, video, audio, and can reason about these modalities together.
Interesting. And then in terms of, oh, we have a question. So I'm going to read it. Are you aware of differences in intent interpretation? So reasoning models interpreting the user query intent like presented with varying thinking and reasoning budget. More of a test time scaling, I would say. This is a question on that.
Yeah, this is a good question. I think
Mhm.
there has been some work here, primarily in the search query intent. Like we saw the use case of Spotify. Similarly, Yelp has also shared their research where they use the LLMs to kind of understand the intent better. They
Mhm.
focus on query segmentation, where let's say even if the query is about find restaurants near me, or let's say a particular restaurant and its reviews, so the model kind of understands the intent when it's referring to the nearby restaurants versus a particular proper noun, and segment the query accordingly. Test time scaling is something that is very challenging in production deployments,
Mhm.
and that's why I think most of the work there is primarily in the academics. And the goal is how do we sort of train the models better early on, and then apply it so that it scales better in the inference.
Interesting. Interesting. So one sort of question in that line. So when we are dealing with VLMs, and if the latency is super important, do you think there are situations in which in production we may drop one modality altogether to just meet that latency requirement?
Yes, I think that's also a trade-off that we would have to
Mhm.
take based on the task. So essentially, yes, depending on the use cases, like let's say there is a use case about user interaction and probably audio is not required, or maybe one of the modalities in terms of other channels are not very helpful. We can definitely drop it so that the model can reason based on the existing ones and be more latency sensitive. So yes, those are some of the optimizations which can be done. But again, it depends on the task performance and if the trade-off is worth it.